Okay, so next thing I'm gonna talk about is the energy in wave. So you probably know, or at least has some, realization that to oscillate, you should have some energy because oscillation is, the combination of potential energy and kinetic energy, right? So if you don't have any energy, then things not gonna oscillate. So for a wave, it's the collection of many things that is oscillating, right? So in that sense, there should be some energy in wave also. Okay, so um, strictly speaking, it's a little bit tricky to write down like what's the energy in wave because you have to combine every particle in the system, and that's not sometimes very straightforward to do that, right? But the only thing we care about at this point is the dependence of energy in wave to the amplitude. Okay, so we're gonna kind of write down not too rigorously, but we're gonna kind of try our best to show that. So the in wave, energy in wave. So if we step back a little bit to the wave in a string again, even though we are talking about sound wave, right? But this is fine because wave in a string also is a valid wave, right? So what's the energy in wave? Well, we know how to calculate energy of each oscillating particle in the system because that's just simple harmonic, right? So I can write something like this. I can write uh, energy E of each particle in the system, okay, E of each particle, which I will call E sub I, okay, which is E of the particle which we label with our number I. So maybe this red dot is the 100th dot in the system, something like that. So this will be E 100, right? And then you have E 101, 102, something like that, right? So but this one is just for each particle, and that's gonna have two contribution. One is the kinetic energy EK plus the potential energy EP. Okay, that's true for any particle in the system, but for now we just look at only one particle. Okay, so what is EK? Well, it's just 1/2 mv square, and v in this case for this particular particle, that's the velocity of the particle. Okay, not the velocity of the wave. It's the velocity of the particle is vy, which is going up and down. Right? So I should write vy here, and write clearly that this v is not wave velocity. Okay, so don't get confused here. This is not wave velocity. This is the velocity of the particle itself. Okay, so 1/2 mvy square plus the potential part. If we talk about like mass and the spring, then it's gonna be kx square. But we didn't use x, right, for displacement. Remember, we use y in this case, right? So it should be 1/2 ky squared, not x squared, because we use x as the location in the horizontal direction. But this is the potential energy of this particular particle, and elastic potential energy depends on the displacement of that particle, which we use the variable y for. Okay, so that's why it's 1/2 ky squared, not kx squared. So make sure you understand the variable here, and I'm gonna label it now here as not x, which is used for position on the string. Okay, not that. Okay, so we use y. And Well, this is the hard part, which we already done, is the setup of the energy, because the rest is just what we have earlier, 1/2 m. What is Vy? Vy is dy by dt, the whole thing square, and then plus 1/2 ky square. And what is y? Well, y is the wave function that we had earlier, a, let's say, sine kx minus omega t. Okay, so we can substitute this in, and the derivative we already did. So there's no problem here, so it's just 1/2 m times dy by dt, so you get a omega cosine kx minus omega t, the whole thing square. Okay, and then plus 1/2 kx square, so 1/2 k, and then a square sine square kx minus omega t. Right. So you can, tidy this expression using some trigonometric identity, but that's not really our focus here. Our focus here is to show you that the energy for one particle here depends on the amplitude square. Okay, the rest I'm not really worrying about at this point, right? So we can just ignore them. So I just write EI, which is the energy of the particle at the location I, is just proportional to the amplitude square. Okay, so the energy of each particle depends on the amplitude square. Now the energy of the total wave, you just need to sum over every particle that you have in your system. And if we assume that every particle has the same amplitude, then the total wave will also be proportional to the amplitude square. Okay, so this is what I'm trying to get at, is that if you double the amplitude of the wave, the energy required to do that is actually 4 times. It's not just twice, okay, because of this amplitude square dependency of the energy. And most of the time, we are not talking about the energy directly, because if we have wave, usually you have the source of the wave. So if we go back to sound wave, you might have like a speaker here, and the speaker is giving out sound wave, right? And usually speaker is giving out sound wave all the time, right? So the speaker is giving out energy at every second. So most of the time it does not really make sense to talk about energy alone, because okay, how long does the speaker turn on? How long is the wave has been going on, right? So instead of the energy, we're gonna talk about the power, the power of the wave, which is the energy total per unit time that the source of the wave, in this case the speaker, is giving out. Right? In any case, the time is just time. It's not going to change the proportionality here. So the power of the wave is also proportional to the amplitude square. And that's the important thing that you need to remember. Okay, so power of the wave depends on the amplitude square. So if you want to double the amplitude, you actually don't need to double the power. You need to increase it by square root of 2 times. Okay, so that's something that you should be aware of. Okay, so next thing I want to talk about is the speed of sound. So the speed of sound, I mentioned a little bit last time already. It depends on what kind of medium that you have your sound wave in. And the one which is most common value that you should know is the air. And that's about 331 meter per second. So most of the time, you can use speed of sound in air, roughly about 330 to 340 meter per second. And it actually depends on the temperature. As you can see in the table here, so air at 20 degrees Celsius is actually faster than air at 0 degrees Celsius. Okay, so if you don't know exactly the temperature, then you can just use some value between these two value here. Okay, and air consists of many different kinds of molecules. I hope you all know this. And I hope you know that even though us as living creature require oxygen to breathe, okay, too much oxygen is also toxic. All right, too little oxygen is of course not good. So in air, 20% is oxygen and 70% is nitrogen, and the rest is just mixture of every other kind of gas like helium, hydrogen, blah blah blah, right? So the reason why air has this particular speed of sound is because of the oxygen and the nitrogen in air. So if you take the oxygen alone, 100% oxygen, which is not air, okay, air is about 20% oxygen, the speed of sound is actually lower because oxygen is heavier than normal air. But if you take now helium, which is very light compared to normal air, then the speed of sound will be way, way, way faster, like almost 3 times faster. And to the extreme, if you take hydrogen, which is the lightest element that you can have in terms of air, then it's going to be even higher in the speed of sound. Right? It's because the molecular mass of this gas, the hydrogen, is a lot lower compared to other types of gas. Okay, and I mentioned earlier that a sound wave can also travel in liquid, right? So if you have different kind of liquid, then you can look at the different numbers of velocity. And in solid, you can also have sound wave travel in solid. So generally speaking, if you have like very stiff, very hard material, the sound velocity will be higher. For example, if you have like metal, it's about 5,000, 6,000 meter per second. But if you have like really soft material, like rubber here, then it's gonna be lower. But it's a little bit hard to predict, given the material, what's the velocity of sound. Um, and it depends on the structure of the material itself, which is really hard to calculate. So most of the time, people will just measure it experimentally, and I believe like these numbers are the experimental value. Okay, so this table might be useful, especially when you need to solve problem which related to speed of sound in different kind of medium. Okay, so this is v, wave velocity of sound in different medium. Okay, so normally if it's in air, then it's going to be roughly about 330 to 340 meter per second. All right. So so for sound, we're gonna like jump a little bit around between different topics because it's just the way it is, because we are used to like a few concepts here and there. For example, like next thing I want to talk about is the loudness of sound. And well, this is actually nothing too complicated, because like a very loud sound, you should probably realize it's just a sound wave with higher amplitude, right? So the loudness is related to the amplitude of sound wave. And so, so how exactly? Well, the loudness is the term that we use kind of exclusively for sound because it's related to how you hear the sound. Um, a more general term is called the intensity, and this one gives you the notion that applies to every other kind of wave, like light wave. Like you have the intensity of light, right? So you have like bright light, you have dark light, right? So high and low intensity. So what is intensity? Intensity is, by definition, is the power over the area. Okay, so it's the power per unit area. The unit is in watts per square meter. That's the intensity. So what area are we talking about? It's the area of your detector. So if we talk about sound wave, you have like a speaker that's giving out sound, and you're hearing this sound. How do you hear it? You hear it with your ears. So your ears acts like a detector, right? So your ears look like this, right? So this is your ear as a detector. And what area we're talking about is the area of the detector. So how large your ear is or are, right, if you use two of them, right? So the reason why we have to divide by the area is that if you compare a large area detector and a small area detector, for example, you have like the you have an elephant which has a really large ear, right? And then you have like a human ears which is smaller, right? So let's say this is elephant ear, and this is human ear. And let's say human and elephant stand at the same point, which is same distance from the speaker. They should hear the same loudness. They should hear the same intensity, right? Even though the total power of the sound wave that is received by the elephant ear is larger, right? It's just because it has larger area. Okay, so we divide by the area is just to take away that area dependence of the detector, right? That's for the intensity, right? So you have larger ear, or you have smaller ear, you should hear the same intensity in that sense. Okay, so that's why it's divided by the area. And one important thing is that what happens if you move your detector? For example, if you have a speaker again, right? And then one moment in time you are standing here. So I'll just put the letter D here as the detector. And let's say the distance is R. And then sometime later you step back so that you increase the distance to be another R. So then R prime, something like this. So everyone knows that you're gonna hear the sound a little bit softer, right? The loudness is gonna be as loud because you are further away from the source, right? So how does this dependence of the distance comes in? Well, if we think about the speaker and if we assume that the speaker is giving out the sound in every direction, okay? So what is the area received by the sound in total? Well, it's actually the area of a sphere which is covering the whole speaker like this. Okay, so in terms of the intensity at, let's say, point A, so the intensity at point A is equal to the total power of the speaker which is giving out sound divided by the area. Okay, and the area we are talking about is the total area of the sphere which is surrounding the speaker. So this area is gonna be, well, what's the area? What's the surface area of your sphere is 4 pi r square, right? And this r is the distance from the source. And the whole exercise is trying to show you that you have this intensity and distance dependence in terms of 1 over r squared. Right? So intensity is proportional to 1 over r squared, not just 1 over r. Okay, because if you increase the distance by 2 times, the whole surface area actually increased by 4 times. Right? So if you have the same power, which you should have because it's the same speaker, you divide by larger area. So you have less intensity in that case. Okay, this is what we call the inverse square law. Which you're gonna see later also in electromagnetic stuff after midterm. But this is important to know because it tells you that the intensity falls as 1 over r squared instead of 1 over r or any other dependence on r. Okay, so that means again, if you, so if we increase our distance away from the source, from the speaker, from r to 2r, then the intensity goes or decrease from I, the initial intensity, to I over 4. Okay, so this is what we see here. And that's also what's happening when you measure this experimentally, right? If you increase this by another 2 times, then the intensity always decreased by 4 times. So it's 1 over r squared. Okay, so it's pretty important. And this is also important, so it's also good to know, right? So if you know, let's say, okay, let's just put in some number. So let's say you have a speaker, and a normal speaker that you use outdoor is probably has, something like 60 watts or something speaker. So that's going to be the power. And then a simple question that I can ask is like, if we are 10 meters away from the speaker, and we assume that the speaker is giving out sound in every direction, right? So we can use this area of the sphere to be 4 pi r squared. Then the intensity will be just 60 watts divided by 4 pi r squared, which is 10 meters squared. So if we put in the number, then we're gonna get something like 4 pi, something like 0.0477, something like this. And what's the value? Where is watt per meter square? Okay, so this is a very simple way of calculating the intensity of sound at any location away from the source here. And we're not going to stop here because in reality, we are interested in the sound intensity or the loudness of sound that we can hear. And we want to have some number to describe like how loud it is. The intensity itself is fine. We can use this number. If this number is high, then it's louder. If this number is low, then it's going to be softer. That's perfectly fine. But the problem is that, and this is coming really just from the engineering point of view, the problem is that the range that we can hear in terms of the loudness is very, very broad. So what I mean is that if we do experiment and then we are trying to find out, okay, what is the lowest intensity that we can hear in terms of the loudness of the sound? Okay, so, well, how do we do that? Well, this speaker giving out 60 watts, you are 10 meters away. you can hear it fine. And then you say, okay, now let's reduce this to 6 watts, to zero point 0.6 watts, to 0.06 watts. At some point, you're gonna stop hearing the sound because it's just too soft. And then you ask like, okay, what's the lowest intensity that we can hear? And it turns out that the lowest intensity that we can probably hear, I call it intensity minimum, right? This minimum means the minimum that human can hear. For other animals, it might be lower or it might be larger. Or if you're getting older, then this I mean will be higher, right? But on average, the lowest intensity that you can hear is actually very small. It's 1 times 10 to the minus 12 watts per meter square. 1 times 10 to the minus 12 is about almost 1 million times lower than that. Maybe like 10,000 million times lower than that. So any intensity between here and here, or even larger than this, they are all audible by human, right? So in terms of engineers that dealing with sound engineering, they don't want to deal with this large range of number. They don't want to deal with 1 times 10 to the minus 11, minus 8, minus 9, something like that. So they want to come up with a more convenient numbering system to describe this loudness. Okay, so that's the motivation of the next thing we're going to talk about, which is called the decibel scale. Decibel scale does not introduce any new physics. It's just another way of writing the intensity, right? That's one thing that I want to be clear. There's nothing new in physics. It's just number playing with numbers. Okay, so how do we use this? The number which we call decibel beta is defined to be 10 times the logarithm base 10 of the intensity of the sound that you want to describe, I, divided by some reference sound intensity, which is the lowest intensity that human can hear. So I mean here is always going to be 1 times 10 to the minus 12 watts per meter square. Okay. And because of the presence of log, right, you don't need to deal with this 10 times 10 to the negative 12, 10 to the negative, or 10 to the whatever, right? Because when you take log, then you only care about that number, right? And the decibel number is a lot more convenient to deal with, at least from engineering point of view, because it's just a number which is short, concise, and describe everything that you want. Okay, so just to demonstrate like how this works, let's take the number that we calculated earlier here. So a speaker of 60 watts, which is the power, and we are standing 10 meters away from the speaker. We have the intensity of this much. Okay, so let's take I equal to, roughly speaking, is 0.0477, but I'm gonna write it 0.05 watt per meter square, like this, just for a demonstration. Okay, and so this is the sound intensity, and let's say we want to convert this intensity in decibel. Okay, again, it's just playing with number. There's no physics law that you have to use or anything, right? It's purely calculation. So let's do that. So decibel beta is 10 times log of 10, not log of 10, log base 10 of I, which is 0.05 watts per meter square, divided by our reference level, sound level, which is I min. Again, this is fixed, okay? You don't need to change it around. It's always 1 times 10 to the minus 12. So let's put that in. Watts per meter square. And one extremely important point is that, and I see this every time um, this kind of problem appear on the midterm, is that you forgot to make sure that the unit inside the log has to exactly cancel each other out. So that means the numerator and denominator has to be in the same unit. In this case, already is, which is fine. So we can cancel out. Inside the log, you should not have any unit left. So you have this number, which is 10 log base 10 of 0.05 times 10 to the 12, right? Because it's 1 over 10 to the minus 12. And if you calculate this using your calculator, then you're gonna get a number which looks a little bit more manageable, which is just 107. Okay, and what do we use in terms of unit? We call it dB, decibel. So 0.05 watts per meter square in terms of the sound intensity is equivalent to 1 over 107 decibel. Okay, decibel actually is just a number. Actually, it doesn't have like a valid unit per se. It's not like you can have like kilogram newtons per meter or something like that, right? Because everything is dimensionless because you cancel out all your units already. So this one is just kind of like a thing to remind you that this is in decibel. So if you want to convert this back to the intensity, which is in watts per meter square, then you have to use this equation, right? So you need to do 10 to the power or whatever, right? So this is how you use it. Another thing I want to emphasize is that if you double the intensity, the decibel level does not double. Okay, that's probably the most common mistake that students do on the midterm. For example, if you double the intensity, so what do I mean? Well, instead of 0.05, you get zero point 0.1 watts per meter square. Okay, you double it. You double intensity. What's the decibel? And some people will just say, oh, it's just twice because it's just 214 dB. That's not true. And you're going to see why, because this line will become 10 log base 10 of twice, right? So it's 0.1 times 10 to the 12. And this is going to give you 110 dB. So you can see that by doubling the intensity, the dB level actually increased by 3. It's not double. All right, it's not double, it's only increased by 3. Okay, so this is like a major difference between using a decibel scale and the intensity itself. Okay, so very careful, be very careful when you calculate this, because believe it or not, you're gonna forget when you do the problems on the midterm. Okay, anyway, well, now we can describe the loudness using this decibel level. So let's look at this chart, which is quite interesting. So to kind of give you the idea of like how different decibel level corresponds to the thing that you are used to. So we have the sound level, which is in decibel, in dB, and horizontal is the frequency of sound, because like how you hear the sound also depends on the frequency. So that's why we plot it like this. But for our purpose here is the vertical axis, which is important here, right? The white area here, that's normally the region where you can hear without causing any damage to your ears. Okay, If you get any louder right here, that's gonna start to hurt a little bit. That's why when you go to the rock concert, you shouldn't stand in front of a really large speaker because the sound wave entering your ear is just too much, okay? And a lot of energy entering your ear, it can damage your ear, and you can have like permanent hearing loss. That's not good, right? So around 112, 120 or something like that decibel. That's probably the loudest that you should you should hear. And if it's briefly, then it's fine. But if over a long period of time, it's like a couple of hours, that's not good. Okay, and you can see that the range of dB that you can hear is actually quite broad, right? So it can go from 0 dB. So 0 dB is the sound, exactly the lowest sound that we can hear, okay, up to 112, which is about 0.1 watt per meter square or something like that. Okay, so so now you can read this chart here. All right. So I only have 5 minutes left, so I'm not gonna start talking about the next topic. So maybe I gonna stop here. And if you have any question before we stop, we can also discuss. Okay. But if not, then that's it for today, and I will see you all on Wednesday. All right. You want to see the first page, like way at the beginning, right? This one. Okay. Try to zoom out a little bit. Okay, guys. If there's nothing else, then thank you all for participating, and then I will see you on Wednesday. All right. So take care, everyone, and I'll see you then.